Lesson 3.2 is all about solidifying our knowledge of slope at a point, which is basically the derivative, or instantaneous rate of change. So really approaching that slope at a point concept from the perspective of what it is graphically, what is its connection to the graph, modeling with the tangent line, and then getting the equation of a tangent line. Notations for the derivative, which is slope at a point. We would say this is f prime of x, or f's derivative at x, or f's slope at x. This is a shorthand way to say this notation right here. Your dependent variable doesn't have to be f of x, it can be y. So this would be y prime of x, y's slope at x, or y's derivative at x. Same thing, shortcut notation. This notation, d for delta, means change of y over change of x, which is again comparable to slope, so slope at a point. This triangle symbol is the delta symbol, so these are equivalent. And then another way to write a derivative is to say instead of dy, you can center the function you're trying to evaluate its derivative of right here. So you can separate the y out to say I'm deriving this function y with respect to x. These two notations have the same meaning. We use them in different places depending on what the input or what is the given of the situation. Both mean the same thing. You're finding the slope of a curve at x equaling 4. Then once you have your slope, you want to be able to find the equation of the tangent line that models the slope at a point. Going back to algebra and pre-calc, this is very familiar to you, point-slope form for a line. But in calculus, we up the notation and use function language. Instead of slope being m, slope is now the derivative. And instead of using x and y, we use a and f of a. First example, I would pause the video, and based on what we have done so far, see how many of these you could get yourself. The value of g prime of x means the slope. So where on the graph of g do I have all of these given slopes? You can start at the top, work your way down, start with whichever one is the easiest, it's up to you. -3 means I'm looking for the steepest negative slope. I have two negative slopes. The part of the curve that looks to me like it's decreasing is here at F and here at C. F is steeper than C, so I'm going to put F here and C here. A slope of 0 is when the graph is going flat. Well, I'm looking here and here. These are on the positive side of the flattening. This is also to the right of the flattening. E looks like it's closest to being on the flat part of the curve. Ordering my positive slopes, I'm going to look for 3 positive slopes that increase in steepness. So the one closest to the flattening is the smallest positive slope. I think that looks like A, so I'm going to put A here. Then I want to compare the slope at D versus the slope at B. And from my little quick tangent line, the slope at D is steeper than B, so I would go B, D. Given that the tangent line to the graph of y equals f of x at the point 2, -5 has this as its equation. Well, what does that mean? We have a point at 2, -5. Here it is. And then what happens is the slope of the tangent line, that means we're touching the curve at this point, and its slope is, we have -6, up 1 over 2, up 1 over 2, So my tangent line to some curve would look like this. All right, well, what's the curve? We don't know what the curve is. We could draw anything we want just to try to model that slope there. All right, it's a slight positive slope, so I tried to get it just before the peak of the curve. What matters, though, is f prime at 2, f's slope at 2. Well, here's my tangent line. It's modeling the slope of the curve at this moment. So I go to my tangent line. Where do I find slope? Slope is in the m spot. So f's derivative at 2 is a half. Given the tangent line to the graph of y at this particular point has the equation. Now this one has a tangent line equation in point slope form. This one had it in slope intercept form. Still the same idea. I want to go to -5, 4, and find the slope. Instantaneous rate of change really means slope at 5. So I want to find the instantaneous rate of change of y. So I'm going to say dy dx at x equaling -5, or you can say y prime at -5. You're really just finding the slope. Well, like the last example, slope is written in a linear equation. It's in the spot for the m. So that means my derivative value is -9. Given that we have a point, this is point notation, this is the derivative, which means the slope at this point. Find an equation for the tangent line at x equaling -4. For the equation of the tangent line, I say y minus f at a, well, that's the point, that's the y value of the point, is equal to, this is m, which is slope. Well, who's representing slope? This is derivative notation. That means this is the slope. And then x minus the a value, or the input value. The input value in all these cases is -4, so I'm going to swap it to +4. The tangent line to the graph of the function f at the point 4, 5 passes through the point -1, -8. Find f prime at 4. Well, here's that point 4, 5. We have some kind of a tangent line that's going to go through 4, 5 and -1, 8. So this could be a representation of my tangent line. Since I'm working with slope at 4, that means there must be some curve that's going to come in and model that for a slope. Oops. So I'm going to come in, model that as my slope, and go back down. Well, if I want to know what is f prime at 4, I need to find what's the slope of this line, because that line is modeling the slope at 4, 5. To do that, since I don't have an equation of the line, I'm going to go back to traditional algebra 1 to find slope. y2 minus y1 over x2 minus x1. I get -3/5 is the slope of my line. Figures not drawn to scale. Applying the pre-calc and calculus skills together, designing a graph. F of 2 is equal to 3. Function notation for a point at 2, 3. This tells me the slope at this point I just drew. Well, if I'm at 2, 3 and I have a slope of 0, that means that the graph is flattening at x equaling 2. Since I don't have other information, I'm going to pause before I draw something, because I could draw a max, I could draw a min, or I could go up, go flat, and then go up again. I have 3 different contenders. So we look at the rest. This is telling me f prime is derivative, which is slope, being greater than 0. So that means positive slope. In terms of curves and sketching, if you have positive slope, that means your function is increasing. So I need to draw something that is increasing if I am greater than 2. That gives me more information. Here I am at 2. I had to flatten, and I need to be increasing after. Well, if I was flattening here, then there's my flat point, and I'm going to come up, and I'm going to start increasing, something like that. F prime, derivative or slope, is less than 0. So I have negative slope. Well, in terms of a function, what does that mean? That means that f of x, if I have negative slope, is decreasing when I'm smaller than 2. So somehow over here, I have to decrease left of 2 and get to that flattening point. So I'm going to just finish it off and say I'm decreasing, getting flatter, and then there's the f prime at 2 equals 0, and there's the increasing. All of this was a fancy way to say sketch the graph of a quadratic function, but in terms of calculus language. Find f prime of x. We're going to start applying the power rule to all of our problems. I have y equals 4x squared, and then actually I'm going to decide if we want to do y prime or f prime. Since this one specifically says f prime and y is equal to f, I'm going to say f prime of x is equal to power rule in action. The power goes in front, multiplies 8x to the first. That is my slope. After I know my slope, then I want to find the equation to the tangent line of my graph. So this is a parabola opening up, so kind of steep, and it's saying over here at -3 there's some tangent line, and my job is to find the equation of that particular tangent line. Again, figure not drawn to scale. So my a value, my input value, is the x value. What I do is I first find out, well, what is its partner, y? So right underneath here, I'm going to say f of -3 equals 4 times a -3 squared would be a 9. So I end up with 36 for the value that goes with my point. The next thing I need, besides a point, which is right here, I also need the slope. So that would be f prime at -3. F prime at -3 is going to be 8 times -3, which is, that's about -3, equals -24. I'm ready now to build my tangent line. In calculus, we use point slope form. It's just, everything just plugs in nicely. Y minus the y value of the point is equal to the slope, which is -24, times x minus our a value, our input value, which was a -3, so I'm going to go to +3. And the two things I was looking for, there's the f prime of x, there's the equation of the tangent line, and the corresponding work to go with it. For the next one, in order to use the power rule, we need to have things written as x to powers. So I'm going to say f of x first is 3x to the 1/2 power. Because in order to apply the derivative, I need to be able to move my power. I need a power. So f prime of x is equal to, move that to the front, multiply it, 3/2 x to the -1/2. Since we're evaluating it at a particular number, it's always good to use those algebraic skills to rewrite it back in an easy form to evaluate. -1/2 means flip the x to the bottom, a 1/2 power put back in the square root. For a tangent line, I need the slope at our given input value, which is 9. So I'm plugging it in here, 3 over 2 square roots of 9. That gets me 3 over 6, which is 1/2. Once I have a point, a slope, I need a point. So I'm going to go back up here and say f at 9. That's 3 times the square root of 9, which is 3 times 3, which gives me 9. This is the y value, the x value, the slope value. Y minus y1 equals slope, which is f prime, times x minus 9. F of x, again, not written as x to a power. First objective is always to get it as x to a power. Then f prime of x, negative 1 times 1 gives me negative 1, x to the negative 2. Again, for the purpose of evaluating, let us put it back into its other form. Find f prime at 2, negative 1 over 2 squared, which is negative a quarter. That's my derivative or slope. Now I need my point. Go back to the original. F at 2 is 1 divided by the input value of 2. Tangent line, y minus the y value is equal to the slope, or the derivative, times x minus 2. This is my f prime. This is my tangent line. Again, f of x is not written with x to a power notation. Convert it first for x to the negative 1/2. Take the derivative using this thing called the power rule. Bring the power in front, multiply it. I get negative 2x to the negative 3/2. This one's a little bit harder to convert, but if I convert it, I have negative 2 over the square root of x cubed. And I like to put it in this form because if I'm evaluating, I would rather square root first and then cube. You can do either one, but we go for the easiest path. F prime at 16 is my target value for slope. Negative 2 over square root of 16 being cubed. That would be negative 2 over, that's 4 to the third, which is 64, reduces to negative 1 over 32. That's my slope. My point, f at 16, is 4 over the square root of 16, which is 4 over 4, which is 1. Y minus 1 for the y value equals the slope value, the derivative value, times x minus the a value. Equation of my tangent line, and then derivative. Both are given. Getting comfortable again with this notation and recognizing all the different ways to say slope. This one now is saying find dy dx. Well, the other one said find f prime of x. We're doing the same thing. We're finding slope. The objective, we always have to have things written as x's to powers. So I'm going to convert it and say 6x to the negative 3. So it goes number x power. Then dy dx, apply the power rule, negative 18x to the negative 4th. And this one we're not evaluating it, so it's up to you. You can keep it in this form, or you could rewrite it as this one. Either format is fine. Y equals mx to the third plus nx minus p. A lot of stuff going on here, but what's key is we are finding the derivative with respect to x. That means x is changing, but the m, the n, and the p are not changing. Those are constants. So it's as if this was a 2 here. So if I parallel it and say if this is 2x to the third plus 5x minus 6, its derivative would be 3 times 2 would be 6. The 2 gets carried along. X to the second. 1 times 5 is 5. So I keep the 5, and this becomes x to the 0. And then that equals y's derivative for this particular example. So if I apply it here, m is a constant, just like the 2, it gets carried along. 3m x to the second plus 1 times the number here, 1 times 5, 1 times n, becomes n. Then it becomes x to the 0, which is gone. And a number by itself, the slope of any number, is your horizontal function. So it's a straight line going across if you looked at it individually, so it goes to 0. Or think of it as x to the 0 to start. 0 times p wipes it out. There are some strategies for analyzing functions and being able to find the derivative graph. Take a moment, pause the video, read through all these, and then follow along with me. I'm looking for the derivative of this cubic function. Well, what do I notice? I go for target points. I'm going flat here and flat here. So that means I have slope of 0 at around a little bit past -3 and then about 2-ish. So I need to look for a graph that's hitting 0 at those 2x values. The next thing, I recognize this is a cubic, so its derivative should be a quadratic. So I'm going to focus now on my quadratics over here that have a slope of 0 just past -3, nope, just past -3, yes, and not past -3. So right here, B looks like a match, because just past -3, there's my slope of 0. At 2-ish, there's my slope of 0. To help me out in between, I could draw some tangent lines. If I go to -5 and draw a tangent line, I've got a positive slope here. Well, if I go to -5, it's saying the slope should be about 3.5. Well, if we draw it correctly, it does look like the slope is about 3.5 at this point. So I'm feeling pretty good about my selection here, that this one's derivative is B. I have a quadratic here, so I go for the 0, excuse me, and that is at 2, 1. It's got slope of 0. It is a quadratic, so its derivative should be linear. So I'm looking for a line that goes through 2 with 0. Well, the two lines that I have both go through to 0. I need a little bit more information. I'm going to go left of that 2, 0, pick a point, and quickly draw a tangent line at that point. I have some positive slope here, and my positive slope is, let's see, here, 1, 2, 3, somewhere between 3 and 4. So at 0, I want to be 1, 2, 3, this one's at 4. So this is my best match. I'm going to say that one goes with E. I have another cubic again, so its derivative should be a quadratic. I go for flattening and flattening. So I am looking in particular for a derivative graph that crosses at -1 and then a little bit past 4. If I look up here at -1, there it is at 0, and a little bit past 4, it's at 0. In between, if I just pick any point in between and envision the tangent line between those two, I'm saying, okay, at around 2-ish, we have some type of negative slope. Around 2-ish, it looks like it's pretty close to a slope of -2. So I'm getting a pretty good match with A. This is my other quadratic. Again, the slope is 0 at 2. And then if we look at 0, it's got a negative slope here. So let's go find the linear function. At 2, at 0, at 2 it's 0. At 0, it's about -4-ish. That does look like a slope of -4, so we're going with C. For 5, another cubic, going for those flat spots again. And those flat spots are occurring at -2 and close to 2. That graph is right here. And if you check in between, I have a positive slope, not very big positive slope, looking at about a slope of almost 1. We've got a match with D. dy dx at x equaling 4 means find y's derivative at 4. these are the same notation. So what I'm going to do is I'm going to go over here first and find y's derivative in general using my power rule. 6x plus 2. Then to find y's derivative at 4, we plug in 4. 6 times 4 plus 2, we end up with a value of 26 for the slope. My next section, now we are going to draw the graphs. So to draw the graphs, I'm identifying slope. This is a linear function. It has constant slope. If I check my rise over my run, rise over run, it looks like it's rising 1 and running 1. So that means the graph of f prime would be a constant function, and it would be at a height of 1. So I would say f prime of x is the linear function at 1. I see a quadratic. The quadratic is having 0 slope at 0. So I know that my derivative graph should be going through 0, 0. Because it's a quadratic, it should look like a linear function. So I just need some kind of a slope to get me started. So if I pick any point I want, let's pick right here at 2, and I'm going to draw my tangent line at 2. And I'm going to say, until I get to a point, it's about here. So this one looks like a rise of 4 and a run of 1. So at 2, my slope is 4. So that means at negative 2, by symmetry, it should be a negative 4. So I'm going to connect my 3 lines, or 3 points, and this would be my f prime of x for that one. Absolute value function is a little tricky because it has 2 unique slopes. But down here, we instantaneously change from one slope to another, and you're changing from a constant rate of change. So what we'll do first is figure out, well, what is the slope on the left side? If I go point to point, it looks like I am going at a rate of down 3 over 1. So until 2, we are at a slope of negative 3. So until 2, slope of negative 3. And then what happens here is you can't instantaneously think of yourself walking. If you walk 3 feet per second forward, can you instantaneously change to the rate of 3 feet per second backwards? We cannot. So what we do is we say that the derivative at 2, so f prime at 2, does not exist. It is undefined. There is no value for the slope at 2. You can't instantaneously jump from one rate to another. On the right side, we're jumping to a slope of 3. So now what I'm going to do is I'm going to go up to 3. 1, 2, 3. Open circle, because we do not have a derivative at 2. And then the rest of the way is my slope of 3. This is f prime of x for C. And then I'm going to do one more, and then I'm going to pause, and we're going to do the rest in class on Tuesday. Slope of 0, right here at about 1, 2, 3.5. So I'm going to put a point there, saying that slope of 0 means the derivative graph crosses here. Up at the top, looks like flattening again. That's a slope of 0, and that occurs just before the 2. Well, what do we need now? We need to know what is the shape of the graph. If this is cubic, its derivative is quadratic. So I'm going to pick a point to calculate slope at. So I'm going to do over here at negative 6. And at negative 6, it's pretty steep. And so it looks like a slope of about, let's see, we're at 4, going down here. So slope about negative 5. So at negative 6, I'm going to go to negative 5. And then the only thing I need to know is how high up am I going to go here? So it's looking like it's pretty linear in this section. I could draw a tangent line, but if you look at it, it's pretty close to being linear. It goes up pretty steep. I go up one block over maybe like a half a block. So maybe a slope of 2-ish. So then I'm going to aim to hit that height of 2. Well, that was pretty perfect. And I'm going to go up, make my quadratic, and come back down. And this is a possible sketch of f prime of x. And then again, we'll do the rest. We'll continue on there from Tuesday.